Start the recording ultimately. So, hello everyone. We have today Professor Subhojoy Gupta from IISc and Professor Sudarshan Gurjar from IIT Bombay will be sharing his talk. Sudarshan, can you take over?
Yeah. So great pleasure to introduce my friend Subhojoy Gupta from IISc, and he will be talking about monodromy of the Schwarzian equation on Riemann surfaces. So Subhojoy.
Thanks, Sudarshan, and thank the organizers for the invitation to speak here. I'm very happy to be part of this series of talks organized by Bhaskaracharya Pratishthan. And today, I hope the topics I'll cover will connect with some of the other themes and topics being discussed, over these trimesters. So here's the topic. Here's the title of my talk. I'll be talking about the monodromy of the Schwarzian equation on Riemann surfaces. And I should mention this represents some joint work of mine with Gianluca Faraco, who might be here today. So although I would eventually want to get to talking about our result, I want to keep this talk largely expository and as elementary as possible. So please feel free to ask questions. Okay. So, by the way, I forgot to also thank the organizers for asking me to speak on this palindromic date, which gives me the excuse to put it down over here. So the title of my talk has Riemann surfaces. Throughout the talk, I'll be talking about Riemann surfaces of finite type, which means it's got some finite genus G and finitely many punctures K, and although so things also work in closed surfaces, we'll see that the punctured case is the one we'll focus on. And this is what also appears historically, historically it came first in some ways that we'll see. Okay, and the closed surface was done in some work a couple of decades back. And these Riemann surfaces will have negative Euler characteristic as well. So, 2 minus 2g minus k is less than 0. This is just to sort of exclude some non-interesting cases. And I'll introduce the Schwarzian equation, and we'll start with a punctured sphere, the Riemann sphere with k punctures. So here sort of k is at least 3 just to have negative Euler characteristic. So it's hyperbolic type. And so let me start with this sort of simplest Riemann surface. So here's the Schwarzian equation on this punctured sphere. And here I'm using this coordinate z, which is some global coordinate on CP1 with these punctures. I can take one of these punctures to be at infinity, so that you're really talking about the complex plane. And so I'm using the global coordinate z that's there. And this is a second order linear differential equation. So u is this unknown function, and q is some coefficient that's given to you. That's holomorphic, except for the punctures where it has poles of order at most 2. And this condition of having poles of order at most 2 is known as these singularities being regular. So, and I'll come, and this will appear again in a little bit. Okay, so yes.
Isn't it called Riccati equation?
It has, this equation comes up in, it's something that comes up in many contexts.
No,
and yes, there is a
Schwarzian is a nonlinear thing. This is the Riccati equation.
Yeah, this might have different terminology and different nomenclature in different places, but certainly yes. If you would like to think of it as the Riccati equation, you can do so. And I think it's in certain contexts it is known as Schwarzian equation. So I'm going to stick with that. But this is something that comes up a lot because this is a very simple second order linear differential equation. I mean, if you sort of move things around, this is also the Schrödinger equation, and so also, right? So it's something that is known in different parts of mathematics and physics and different names. Okay. So one thing I should point out, I've written here as a note, is that this coefficient q is not quite a function. You should think of it as a quadratic differential. And this is because you want the pole at infinity. Remember, we've kind of arranged one of the points to be the point at infinity. You want the pole at infinity to also have an order at most 2, so a regular singularity. And to do that, you need to kind of have a change of variable of z goes to 1 by z and work with that. But that changes this whole second order differential equation. It transforms like a 2-0 tensor, which is a quadratic differential. Okay, and so this q is really a holomorphic quadratic differential with poles of order at most 2 at the punctures. And just as a quick example, so here if you have this coefficient 1 upon z, I mean that looks like an innocuous function, but this in fact has this particular Schwarzian equation has an irregular singularity at infinity. So okay, so
QZ dz square.
Yes, that's right. Yeah, so you should
an intrinsic meaning.
Yeah, that's right. That's right. Yeah, QZ dz squared. Yeah, I should mention that here. So the quadratic differential QZ dz squared. Okay, so this is what transforms correctly with when you change variables. So this is what makes the whole equation transform correctly. All right. So as was mentioned, this Schwarzian equation appears many places, but sort of historically, maybe one of the first sort of examples, classical example, is the Gauss hypergeometric equation, which is an example of this form that I wrote down, and that's on this thrice punctured sphere. Okay, so, and you can choose these 3 punctures to be 0, 1, and infinity.
So Subhojoy, just a
yes.
quick question. Quadratic differential means a section of kx square, right?
Yeah, that's right. Yeah, exactly. Yeah. So when I say dz squared, yeah, so the dz tensor dz, it's a holomorphic section of the square of the canonical line bundle. Okay. So what are the sort of basic things about this linear differential equation? Well, since it's a second order linear differential equation, you can always solve it locally. So here, let's say I choose a base point z0. There's going to be linear there's going to be some series that you can write down. So you can formal power series if you like. That's where this regular singularity condition comes in, and you always can define solutions locally, and in fact 2 linearly independent solutions locally. And so you can choose solutions to have a prescribed value and a prescribed derivative at that base point, and you can have a germ of a solution in a neighborhood of that base point. Okay, and so these solutions, in fact, I mean, so this alpha and beta that we chose can be chosen independently. So these solutions, they span a vector space of dimension 2. It's a vector space because it's a linear differential equation. If u0 and u1 are solutions, then so is any linear combination. So there is this vector space isomorphism of this space of germs of solutions with the 2-dimensional complex vector space, right? And once you have these solutions locally, you can analytically continue them along loops, right? So you can, so let me try to draw some circles here. So you can start with around Z0 and this neighborhood Z0, and you sort of keep analytically continuing the solutions along the loop. And if you started with U0 and U1, this basis, these might, once you come back to the original neighborhood of the original base point that you started with, these might become some other linear combinations, right? So it might be so U0 might become A0, let me just zoom in, A0 plus B of U1, where A and B are complex numbers. So it's a different point in that vector space. And this is some C plus D U1, right? And so this change along loops is recorded by a matrix. So once you chose that basis U0 and U1 initially, so you can so this transformation would take this loop to this matrix A, B, C, D. And this is going to be an invertible matrix, because if you go around the loop in the other way, you'll just get the inverse. And it turns out that this is also only depends on the homotopy class of this loop gamma, which goes going around the punctures. And you get this representation called the monodromy representation of the fundamental group to GL2C. And this, I should also mention, is defined only up to conjugation, because after all, to get this matrix, we had to choose this basis U0 and U1. And also we chose a base point to start off with anyway. So we get this monodromy representation, and the basic question, okay, well, before that, I should just say that, so here kind of the most basic example is these two functions, log z and the constant function 1 these two are sort of, they are solutions of a certain second order solutions of a second order linear differential equation on the punctured plane, or if you like CP1 with two punctures, 0 and infinity. And so there is a monodromy around 0 that you can sort of compute. And it turns out that when you sort of analytically continue the solution log of z around the loop, this would go to log of z plus 2 pi I plus this constant. And this is recorded by this, you can think of it as as this change of basis, as this applying this matrix. And so this is a sort of the simplest example of some non-trivial monodromy when you start with the second order linear differential equation. Okay, so before I say what the basic question is, we will also do one more thing. We'll, instead of looking at C2 as a vector space, we're going to projectivize and think of ratios of these germs of solutions. So instead of U0 and U1, I'm going to look at U0 divided by
what is the differential
U1.
equation? Can you write down?
Yeah, I won't write it down right now, but it's not too hard. I mean, one has to take a second derivative, and it's not going to exactly look like this, because there's going to be a U prime term, okay? But after a change of variable, you can you can try to make it like this. Okay, so that's why I try to avoid it. Yes.
It was mentioned in the first talk of Wenke's in the first semester, this differential equation, whose solution they correspond to.
Yeah, that's right. Yeah, so thanks. So it's an exercise, I would say, maybe. All right.
Right.
Okay, so right. So here's the basic question. Okay, so before that, let me just say that I'm going to projectivize. So I'm going to talk about this ratio of solutions and analytically, when you projectivize, this monodromy would now become a homomorphism, a representation of the fundamental group to PGL2C, which I'll also think of as PSL2C. The two are the same. You work with complex numbers. All right, and here's the basic question. So what representations do you get? And this is what I'll talk about the answer to this in this talk. And let me just mention a more general context of, instead of second order linear differential equation, you can talk of a linear system. A first order linear system, like I've mentioned here, where this time the unknown y is like a complex valued vector. And that's the unknown, and A is some given coefficient matrix with meromorphic entries and at most simple poles. That's the sort of the analog of regular singularities. And you can talk of the monodromy, and this time it will be a representation to GL NC. And the question of what the representations arise is the Riemann-Hilbert problem. It's one of Hilbert's problems. And the solution to this was done in a much more general context, not just for punctured spheres or Riemann surfaces, but for other complex manifolds. And I won't talk about that, but this is something that's sort of been solved by Deligne in the 1970s. Okay, but here, although the Schwarzian equation, like I wrote down, can be thought of as a linear system of rank 2, it's a linear system of very specific type. Okay.
So just one small comment that
yes.
the solution of the Riemann-Hilbert problem, yes, in full generality it was solved, but it was, the first one was the Roll and Bollebrook.
Yeah, that's right. It has a very interesting history. It was, it was claimed to have been solved much earlier, but then there was some counterexamples later. But I should mention, yeah, so Deligne's work is in a slightly more general, more abstract context.
That's right.
Yeah, so it might not really answer the specific question that I just mentioned here, let's say in the terms of context of punctured spheres.
Mostly they attribute the solution of Riemann-Hilbert problem was solved by.
Yeah, so maybe I shouldn't. Okay, thank you, though. So in this context of let's say punctured spheres, maybe it's Bollebrook.
Right,
yeah, thank you. All right. So in the and this is in the 1990s.
Right. Yeah.
Okay. Yeah, thanks. All right. Okay. So our basic question now is that. So here we're still talking about punctured spheres. So if you have Schwarzian equations on the punctured sphere, and I'm allowed to sort of, I should mention that. So you're allowed to vary these punctures. Okay, so these are sort of k points on a punctured sphere, and you're given some quadratic differential with poles of order at most 2 at these punctures. You can compute the monodromy and what is the image of this monodromy map. And in fact, Poincaré observed that the dimensions of these two spaces on either side match. I'll skip the computation, but it's a simple enough dimension count. And let me just mention that sort of for the interested listener, this dimensions on both sides, complex dimension turns out to be 3k minus 6, where k is the number of punctures. Okay, so it's easier to see it on the right-hand side, I suppose, because representations of this punctured spheres is representation of the free group on k minus 1 generators, and that's given by k minus 1 matrices, but you're quotienting by conjugation. So anyway, this will give you 3k minus 6. And so based on his observation, he kind of proposed, he asserted that, in fact, that this map is basically onto, right? He said, and in general, one can find a Schwarzian equation without apparent singularities. I've just translated this portion of his paper, and this word in general is in italics, as you can see. And you can find a Schwarzian equation without apparent singularities with a given monodromy. So he kind of claimed it just because the dimensions of these two spaces were the same. And he didn't give a proof of this. And so this is what we also kind of clarify later through our result. By the way, here the word apparent singularities, let me just define it. It will appear later on also in my sort of theorem, in our theorem. So a point P, one of these punctures, is going to be an apparent singularity if one of these solutions actually extends to a holomorphic, holomorphic function at that missing point as well. Okay, and it turns out this is equivalent to saying that the monodromy around that puncture is trivial. Okay, it's the identity matrix in PSL2C, if you like. Okay, and we'll talk about this main theorem, which characterizes the image of the monodromy map with or without apparent singularities. We have sort of both versions. We can allow apparent singularities, or we can not allow it. And so we answer this completely, and not just for the punctured sphere, but on any Riemann surface of finite type. Finite. Let me just mention finite type, but everything is going to be okay. And so before we go on, let me just sort of quickly say what it means to solve the Schwarzian equation on any Riemann surface, because now you don't have a global coordinate, z coordinate to work with, right? So, but you do have a global z coordinate if you pass through the universal cover. So if you give me a holomorphic quadratic differential on that punctured Riemann surface with poles for at most two of the punctures, I can pass through the universal cover and write down the Schwarzian equation that we had before there. But this time the coefficient q, the coefficient is q tilde, which is the lift of the quadratic differential to the universal cover. You can think of this universal cover as the upper half plane, because I'm only sort of sticking with hyperbolic type surfaces, right? Now, in this universal cover, you can once again, talk of solutions, local solutions around the base point, and these can now be analytically continued to the whole of the universal cover, right? So there are no loops now in the space. Right? So you have a well-defined map. Solutions now, U0 and U1, and you can take the ratio like we were doing. This will now be some map to CP1. And where does the monodromy come in? Well, remember that deck translations act by biholomorphisms on the space. So if you analytically continue along an arc that's a lift of a loop, let me just quickly draw a Riemann surface. Maybe it has some punctures. And if you have a loop in this space, let's call it gamma, based at wherever the Z0 projects to, then as if you, so this arc upstairs is the lift of this loop here, which is a non-trivial element of the fundamental group. Now, this Z0 and gamma of Z0, they differ by a deck translation. And since it's a biholomorphism, and this coefficient q tilde that we have here is invariant by deck translations. It's just the lift of the holomorphic differential downstairs. So the germs of solutions at Z0 and gamma Z0 are exactly identical. So there's locally, these two points look exactly the same. You can think of them as the same vector space. So when you analytically continue to solutions, let's say U0 and U1, and reach gamma of Z0, you reach some other linear combination in that same vector space. And this is where this monodromy comes in. And so you get, so in fact, so this map F that we had is equivariant with respect to a representation, and this for all x in x tilde and gamma in pi1 of x, where this rho is our monodromy representation. Okay, so this time again it's PSL2C. So this makes sense, even how I introduced it, it also makes sense on any, Riemann surface. And the question is what representations arise in this more general context. And I should mention here that, and this is what we are going to answer for punctured surfaces, but in the closed surface case, this was done earlier. This is the work of Gallo, Kapovich, and Marden in the year 2000. We'll be talking about the punctured case. So the punctured case was left, although this is what punctured surface, as I explained, is somewhat more classical, but this was left unsolved. I mean, they mention it as an open problem. Their techniques don't work for punctured surfaces. And this is what we solved. And their approach, as well as ours, is to use complex projective structures on surfaces, also called Mobius structures on surfaces. So this is what I'll now introduce. So these are certain geometric structures. So I can define it this way. So it's like a local system, if you like, the CP1 structure or a Mobius structure. Let me just mention this is also sometimes called a Mobius structure or a complex projective structure. On a surface is an atlas of charts to CP1, so that the transition maps on overlaps are automorphisms of CP1. So these maps on this shaded region here that's a Mobius transformation. This is of the form AZ plus B, CZ plus B. Okay, and so locally this Riemann's the surface looks like it's a projective line, and it's a CP1. Okay, so it's a geometric structure modeled on CP1. And notice that also that since these transition maps are holomorphic, this also gets a Riemann surface structure. So you can think of this as a special atlas on a Riemann surface. And it turns out that it always exists, because any hyperbolic structure on a Riemann surface, which exists by uniformization. Here we are talking of surfaces of negative Euler characteristic. So these hyperbolic structures are examples of complex projective structures. And in a hyperbolic structure, the developing, I didn't get into developing, but you can think of the hyperbolic plane as a subset of CP1 like this. Okay, so it's like the upper hemisphere, if you like. And this time for a hyperbolic structure, the transition maps actually lie in PSL2R. Okay, so these preserve this upper hemisphere. So it's a special example. So there are already plenty of examples of complex projective structures, but there are more, which I'll explain in a minute. And as I just mentioned, the pair of words, geometric structure. This is an example. It's a special case of a much more general notion of a GX structure on a surface. So G is a Lie group and X is some homogeneous space in which it acts. You can sort of model, if you take a two-dimensional homogeneous space X, you can talk of GX structures on a surface, and you can have GX structures on manifolds. And this is a notion goes back to Cartan, Erisman, and Thurston. Okay. All right, so given a CP1 structure, one can also have a global description. What I described was more like a local description in terms of charts on the surface, but you can, in fact, piece together the charts to build a more global map to CP1, but you can do so in the universal cover. Okay, so you can. And that's called the developing map. And this developing map is equivariant with respect to a monodromy, or also called holonomy representation. So you build this developing map by piecing together the charts to CP1. The problem is once you go around a loop on the surface, the two charts might differ by an element of PSL2C, and that's captured by the holonomy of that curve. So somehow monodromy representation encodes how you wrap up this this developed, so the image of the developing map. Okay, so it's equivariant, where I should probably mention. So on the left-hand side, you have an action of the fundamental group.
So Subhojoy,
yes.
I think we are not able to see anything that you are writing. Are you writing something?
Yes, I am. Oh.
The last line we can see is use complex projective structures.
Oh, oops. Okay, so let me try to share.
I'm sorry, I should have said it before.
No, that's fine. Let me try to share it again, perhaps.
Yeah, we just saw it at the end.
Oh, maybe it's taking time to load. Let me try to share it. Okay, so now the screen mirroring is not working. Okay, so now can you see?
Yes.
Okay, fine. All right, so I was just introducing the notion of a CP1 structure or a Mobius structure, and this was a picture. You had an atlas of charts to the Riemann surface, from the Riemann surface to CP1, right? And this is like a special atlas on the Riemann surface, and some examples are hyperbolic structures, okay, because that's a special example, and this is a more sort of a specific case of a more general notion of a geometric structure or a GX structure. Okay, and you can piece together these charts to build a developing map, what's called a developing map. It's an immersion from the universal cover to CP1, right? Piece together these local charts, this developing map is equivariant with respect to a certain representation called the holonomy representation or the monodromy representation of the CP1 structure. Okay, and this equivariance with respect to is with respect to the pi1x action on the left and the action by the image of the representation with some Mobius group on the right. Okay, right. So this is like a global description of this local picture that we had before. And let me mention a few examples. One is this hyperbolic structure, which I said were examples. In this case, in this global description, you see that this developing map is actually a diffeomorphism from the universal cover to the upper hemisphere, which you can think of as the hyperbolic plane. And these representations, these holonomy representations, are Fuchsian representations. They are discrete, faithful representations. Okay, but there are more examples. So here's another that I've just sketched. So here, these are called Schottky structures. These are representations which are actually images are free subgroups of PSL2C, and these, the developing map becomes a diffeomorphism from the universal cover to the complement of a Cantor set, okay, which is the sort of the limit set in this case. Okay, so these are also actually discrete representations, although not faithful. So these are, so you can think of the complex projective surface here as a quotient of CP1 minus this Cantor set by some group acting properly discontinuously and nicely on this domain. Okay, but in general, it could be pretty complicated. The holonomy representations need not be discrete, and you can build more examples. You can take some domain in CP1, let's say a circular polygon, and you can identify sides by Mobius maps so that you get something that's topologically a surface, and you would have this resulting surface would have a CP1 structure, except maybe at the vertices of this polygon. And so these are the possible singularities, but this is going to be the way that we'll later on construct complex projective structures with these regular singularities. So what's the connection with Schwarzian equations? Well, we already saw some connection because we had this developing map, this and this equivariant with respect to representation. This should remind you of the Schwarzian equation. And in fact, there is a connection. There is a bijection between Schwarzian equations on the Riemann surface X with complex projective structures on X. And so one direction we kind of already saw, except I didn't tell you why this map that I constructed is going to be an immersion to CP1, but it is. All right, so that's the idea of the proof, at least, of this direction. And the other direction, so remember, to get to a Schwarzian equation, we want to get that coefficient, in this case, this Q tilde, which is this invariant quadratic differential on the universal cover. Right, so once you have this CP1 structure on X, you have a developing map, and it turns out that you can recover this coefficient Q tilde, I should say, by taking the Schwarzian derivative of this developing map. Okay, that's going to be some invariant pi1s invariant object in the universal cover. And I should mention here that, as I've written here, that you see here sort of choosing a uniformization of the Riemann surface. I'm choosing X to be a quotient of H2 by some Fuchsian group gamma. So and one can check that this Q tilde would be gamma invariant. Anyway, and it turns out this other direction is precisely the sort of inverse of the first direction. Okay, and that's a sort of an exercise in differential equations. And so there is this connection, but we are going to be interested only in regular singularities. And so let me say that Schwarzian equations with regular singularities are in bijection with complex projective structures on X. And the fact that it's a regular singularity means something about the developing map near the punctures. And this developing map near the punctures is going to kind of look like, well, I should mention here, this is going to descend to the surface. I'm going to think of, and I'll have an example in a minute, sort of what this developing map looks like as a neighborhood of the puncture downstairs. And this neighborhood of puncture downstairs is one of these two forms. And I'm going to call them either a cone or a cusp. Okay, this is not standard terminology. This is just for this talk. Right, and it turns out that the monodromy around a cusp is going to be parabolic, a parabolic element of PSL2C, and around a cone, it's going to be either an elliptic element or the identity element. Okay. Okay, so here are a couple of examples just to illustrate.
So
yes.
Sorry, one little thing. I'm not
yes.
sure of the definition. So the higher genus Riemann surfaces minus some punctures, do they CP1? They don't admit CP1 structures, is it?
Yes. I mean, so this bijection is for any Riemann surface. It need not be compact or closed. Okay, so it's an open Riemann surface. So all I need is some, some holomorphic invariant holomorphic differential, gamma invariant holomorphic differential upstairs, right?
So every open Riemann surface admits a CP1 structure? No.
Yes, so here I'm talking about punctured Riemann surfaces of finite type and hyperbolic type. So if you uniformize them, then they'll certainly have a hyperbolic structure, which is an example of a complex projective structure.
Okay.
But there are more, because once you have a hyperbolic structure, then you can choose some gamma invariant quadratic differential, or a lift of a holomorphic quadratic differential that will give you another CP1 structure. And so there's so CP1 structures on X on a fixed Riemann surface, even if it has punctures, is sort of one-to-one correspondence with holomorphic quadratic differentials on the punctured surface. So right now, I mean, it could have very bad singularities at the punctures. It could have essential singularities, perhaps, these holomorphic quadratic differentials, but we are only interested in the ones which have poles of order at most 2. And so we are going to sort of restrict ourselves to regular singularities. And on the complex projective structure side, this corresponds to certain conditions on the developing map, which I've tried to describe here. Okay. And these conditions we can see in some examples. So for example, if you have a hyperbolic structure on a surface with punctures and Riemann surface with punctures, these punctures, we can choose a hyperbolic structure where the punctures look like cusps. And so cusp is, you can think of it as a quotient of H2 with the parabolic, this translation, Z goes to Z plus 1. And in this case, the developing map you can think of is, developing map is just the identity map and sort of viewing things on the upper half plane. Upper half plane goes to the upper half plane, if you like. And so the Schwarzian derivative is actually just the constant quadratic differential. And one can check that, that descends to a pole of order 2 at the puncture. Once you sort of uniformize this cusp to be a punctured disk, this quadratic differential, the constant quadratic differential dz squared on above, it descends to something with a pole of order 2 downstairs. Okay, so this is one of the examples that falls in this the category we are looking at. There are other examples. For example, if you can talk of spherical cone metrics on a surface. So here I've drawn surface to be a genus 0 surface, but it could have higher genus. And this is what's a spherical cone metric? This arises in various parts of mathematics. It's a Riemannian metric of curvature plus 1, except certain points which are cone points. There's a cone angle 2 pi alpha I. Okay, so alpha I are the some real numbers, positive real numbers prescribed there. And so this you can think of as a complex projective structure as well, because the developing map of such a structure, you can think of any sort of metric which is curvature plus 1. Locally, you have this local isometry to the round sphere, but you can think of it as a developing as a map to CP1. You can think of round sphere as CP1 instead. And then so this way, these spherical cone metrics also examples of complex projective structures. And it turns out that these points, the developing map, are of this cone form that I described. So this is one of the reasons for calling them cone. And if you compute the Schwarzian derivative of a map like this, and that complicated formula that I showed you, that has a pole. So this quadratic differential has a pole of order 2 as well. Okay, and with the coefficient of that order 2 pole depends on this alpha I. Okay, and these examples are also sort of not hard to construct. You can take branched covers. You can take a branched cover of CP1. And so Riemann surface with a branch covering from CP1, and we'll revisit this idea later, and this will acquire one of these spherical cone metrics with integer multiples of 2 pi as the cone angles. Okay, so once you have a branched cover. Okay, so anyway, so there are plenty of examples of this of elements in the space of complex projective structures with cusps or cones. And we are interested in this question. So this is now equivalent to that question we started with about the Schwarzian monodromy of the Schwarzian equation. So what are the holonomy representations or the monodromy representations of such complex projective structures? Okay, and let me just sort of just say that you can think of this space of complex projective structures. You can think of that as a bundle over Teichmuller space where so every point in Teichmuller space represents, let's say, a hyperbolic surface maybe with cusps at the punctures. And so the fiber, as we described earlier, is a space of quadratic differentials with poles of order at most 2 at the puncture. So you can think of it as this is like a bundle over Teichmuller space with fibers is these vector spaces of holomorphic quadratic differentials with poles of order at most 2. And so the map we are interested in is sort of the map from this space to that. So in particular, we are allowed to vary the complex structure on the surface as well. Okay, so we're interested in what all representations do you get when you vary the complex structures and these quadratic differentials. So let me say what the answer is for closed surfaces. So this was the work of Gallo, Kapovich, and Marden. So before I state the result, let me just recall this notion of an elementary representation. So a representation from the fundamental group of a surface to PSL2C. So now I'm talking about a closed surface of genus at least 2. It's said to be elementary if there is a set of 1 or 2 points in H3 union CP1. So remember, the PSL2C is also, the set of isometries, orientation preserving isometries of hyperbolic 3 space. And in that model, you can think of CP1 as the conformal boundary at infinity. And so the image of this representation would act on this closed ball. And if there is a set of 1 or 2 points, which is preserved, globally preserved by the image, then we'd say it's elementary. I said preserved and not fixed because if it is 2 points, I'm allowed to have certain elements that swap the 2 points. Okay, so that's the notion of elementary representations. It's also virtually abelian. Okay, so it's abelian up to finite index. The images of these representations would be virtually abelian subgroups of PSL2C. And the theorem of Gallo-Kapovich-Marden is that, if you start with a closed surface representation is the monodromy of some complex projective structure if and only if it is not elementary. So it's non-elementary and it lifts to a representation to SL2C. So the fact that these are necessary conditions is actually not so difficult. For example, the fact that it lifts to a representation to SL2C, we already kind of knew because we saw that we get these representations by projectivizing the monodromy of the Schwarzian equation, which is already to SL2C. And so the difficult part of this theorem was actually the if direction. So if you're given a representation which is non-elementary and lifts to SL2C, how do you construct a complex projective structure with that given representation? Okay, so this is the difficult part. The only if part direction is actually easier. It's some basic topology. And here's an example. If every element fixes 2 points and is a rotation of the sphere, so rotations are also elements of PSL2C, Mobius transformations, then you can think of it as charts to the round sphere and transition maps being isometries of the round sphere. So the surface would require a spherical metric, but that's not possible if you have a closed surface of genus at least 2. Okay, so this is one example, and you can have similar sort of reasonings for sort of where the image of the representation fixes 1 point, or other cases of fixing 2 points. So the fact that it cannot be elementary is somewhat easy, and the difficult part, Gallo-Kapovich-Marden, was the if direction. Okay, so now now that I've talked about the closed case, let me now say what we did for the punctured case. So here's the analog. Here's the definition: is an analog of elementary representations in the punctured case. So now your S is going to be a punctured surface of finite type, like we were saying. It's said to be degenerate if there is a set F or 1 or 2 points now on CP1, which is preserved by the image, and you have some more conditions that for peripheral elements, the loops around the punctures, you need to not just preserve the set, but you need to fix it. Okay, so if it is 1 point, then every peripheral element has monodromy, either parabolic identity. and otherwise, sort of 2 points, it fixes it, and not just preserves. Okay, and that's the notion of degenerate, and non-degenerate means not degenerate, of course. Okay, and I should note that degenerate automatically implies it's elementary, because you have a condition of fixing 1 or 2 points globally, but the reverse implication does not hold. There are elementary representations which are not degenerate. Okay, and here's the main theorem. So this is joint work with Gianluca. So here we are in the setting of punctured surface of negative Euler characteristic and at least one puncture. This arises as the monodromy of a complex projective structure if and only if one of the 2 conditions hold. Either it is non-degenerate, okay, which, as I said, also includes certain elementary representations, or it is degenerate, but in that case, you need to have at least one apparent singularity. Okay, these are singularities, as I mentioned, with monodromy trivial around it. So punctures with trivial monodromy around it. Okay, and there are exactly two families of exceptions. One is when you have a trivial representation and you have either 1 or 2 punctures and the genus is positive, or you have a representation with those images, a finite order group of order 2 group, and you have 1 puncture. Okay, so these are the 2 sort of exceptional 2 exceptions, and otherwise, so you always have. So this is an if and only if statement. Okay, so this is what answers the question I talked about at the beginning about even the monodromy of the Schwarzian equation. I should also sort of maybe mention that part of this, so the case without apparent singularities was some work that sort of also appears with some more discussion that appeared, was published last year. But in this gives a more complete answer. So in the case of no apparent singularities, sort of clarified Poincaré's remark, and he was interested only in the case of without apparent singularities, as was, sort of as he mentioned in his paper. But in fact, so we can give a sort of more complete answer. All right. Okay, so let me mention a few things about the proof. So first of all, you can ask.
Subhojoy,
Yes.
Here you do not include the condition that the representation lifts to SL2?
No, so that's kind of automatic now. That's a very good point. For a punctured surface, you're looking at a representation of the free group to PSL2C, and the space of such representations is automatically connected. It's so you're actually looking at PSL2C to the power whatever the number of generators of this free group is. I think it's 2G minus K plus 1 or something like that. Okay, so it's actually a connected space, and so it automatically lifts to SL2C also. So yeah, I forgot to mention the obstruction to lifting is like a Stiefel-Whitney class, which actually sort of is a characteristic of the component in the representation variety that these contained in. So in the case of closed surfaces, there are exactly 2 components, and in this case, it's actually is 1, and these representations, you can lift it to SL2C. It's a free group after all, so you can assign it any lifts of whatever the generators map to. Okay, so all right. Okay, so let me just talk about what happens to trivial representation, where everything maps to the identity element. So it's a rho of gamma is the identity element for all gamma in pi 1 of S, right? S is our punctured surface, and according to our theorem, you can get it as long as you don't have just one or two punctures and positive genus. So for example, if you have genus 0, then it's easy to create such complex projective structures because you just take the standard complex projective structure on CP1, right? And then introduce punctures. And these punctures would all be apparent singularities. You can actually fill them in. So the developing maps are actually sort of extend over the punctures, if you like. But still, I mean, if these are sort of, this is going to be an example of a punctured sphere with a complex projective structure and trivial holonomy. And in general, you can take a branched cover of CP1 branched over 3 points, and this is where let me just I just drew a picture, but let me just write that. So consider a branched cover. So this is when you have at least 3 points. I'll just stick with exactly three punctures, because you can always, once you have a puncture surface, a projective structure with 3 such singularities, you can always puncture and create additional singularities. So consider a branched cover of CP1 with exactly 3 ramification points. So if you can do that, then you do have an example with trivial monodromy. And this, sort of is one instance of problem that was solved by Edmonds, Kulkarni, and Stong. This is a case of prescribing, finding branched coverings with prescribed branching data, and which is solved, it's unsolved in the genus 0 case, if you sort of look at branched covers of the sphere to CP1. But in the case of positive genus, this was solved by Edmonds, Kulkarni, and Stong. And it's, I mean, one can also explicitly try to construct such branched coverings with exactly 3 ramification points. And one can do it as long as the genus is positive. Okay, and it turns out that these are the only ways to create a complex projective structure with trivial monodromy. One can prove that, and that's why K equal to 1 and 2 and positive genus cannot arise. These are the exceptional representations, because you cannot have a branched covering of a genus G surface CP1 with less than 3 branch points. You can use the Riemann-Hurwitz formula to rule that out. Okay. All right. So that's a trivial representation case. Maybe I'll spend a little bit of a few more minutes. I don't know how long I have. But I'll talk about non-trivial, what happens for non-trivial representation. And it turns out the proof divides, just like in the statement of our theorem, into the non-degenerate and the degenerate cases. Okay.
The developing map can be surjective on the sphere, right?
Yeah, that's right. That's right. Yeah, the developing map is just an immersion. Yeah. Right. So it can wrap around the sphere many times as well. Right, it can be, pretty bad. It need not be an embedding.
Does that cause any problem does that cause any problem, special problem?
No, it's fine. Yeah. So I mean, I just care about the developing map being an immersion, and I need not worry about whether it's an embedding or any other thing. So yeah. Okay. But certainly, I should have mentioned that there are very interesting examples where the developing map is an embedding. I mentioned one, which is the Schottky structures. It embeds as an open domain inside CP1, but there are others which are obtained by perturbations of the Fuchsian structures or the hyperbolic structures, which are called quasi-Fuchsian structures. And so there also the developing map embeds, and the holonomy is in fact a discrete representation. So in any case, yeah, in general, I mean, the developing map could be very wild. Okay, so here are some ingredients of the proof in the non-degenerate case. And it turns out one of the things we use is this notion of framed representation. So this appeared in the work of Fock and Goncharov in a slightly more general context. around the year 2000, I think. And this is some additional, data apart from a representation to PSL2C. Also, this is for a punctured surface, first of all. So I should mention they were working mostly with punctured surfaces. And you have some additional data of points in CP1 or flags in C2, if you like, with every puncture. Okay, and this, if you lift to the universal cover, it gives you what is called a framing. It's a row equivariant map from the fairy set, which is a set of lifts of the punctures. If you think of the punctures as lying in the ideal boundary of the surface that lifts to the ideal boundary of the universal cover. Once again, you can think of fixing a hyperbolic structure on a finite volume, if you like, on a finite area on this punctured surface and working with that. So I should mention punctured surface with negative Euler characteristics to make that more possible. And so this fairy set can be defined, and you think of this not just a representation, but a representation with a framing. And you can talk of the moduli space of such representations. And Fock and Goncharov gave certain birational coordinates on this moduli space using complex cross ratios. Okay, and I'll just maybe sort of say that very briefly. It turns out that these complex cross ratio coordinates are defined with respect to some ideal triangulation on the surface, which you can lift to the universal cover to get some pi1s invariant triangulation. And for every edge in this lifted triangulation, you can define the complex number associated with that edge called the Fock-Goncharov coordinate. And this is just the complex cross ratio of where the four vertices, ideal vertices map to. Remember, there's a map, the framing is a map from this picture to CP1, which is row equivariant. And so these 4 points at the four corners of this quadrilateral, you see here map to four complex numbers of 4 points in CP1, and you take their cross ratio. This can't always be defined. You want these 4 points to be distinct. So that's why you get birational coordinates defined on some Zariski dense open Zariski open set, and that's these Fock-Goncharov coordinates. So there's these non-zero complex numbers associated with each of these edges of the ideal triangulation. And the way that non-degenerate representations come into the picture is a consequence of this work of Allegretti and Bridgeland, which is also very recent. And they show that for a non-degenerate representation, there exists a framing so that the Fock-Goncharov coordinates are well defined. Right? So they have a nice combinatorial argument for this. And what we could do is to use this Fock-Goncharov coordinate, these Fock-Goncharov coordinates of the non-degenerate representation to construct this row equivariant immersion. So remember that to get to a CP1 structure, we only need a row equivariant immersion, and then it would be a CP1 structure with monodromy row. All right, and so the way that this immersion is defined is to first define it in the interior of hyperbolic space so we get this row invariant map called the pleated plane from the universal cover to H3. And this is obtained just by filling in a totally geodesic ideal triangle in H3 for every 3 points on CP1 that you get via the framing. Okay, and once you have it in the interior, you construct an immersion to CP1 by looking at the shadow of these triangles in the boundary at infinity. And there's a little bit of work to be done here because these shadows might not exactly align. So you have to fill in the gap by some region which I've shaded in dark here. And these regions might also wrap around the Riemann sphere some number of times. Okay, so this is sort of a rough idea of how we use Fock-Goncharov coordinates to build these CP1 structures. Of course, there are many things under the carpet now that have shoved them there. For example, one has to prove that these structures have regular singularities and things like that, but I won't talk about it today. Already out of time. I'll just quickly mention that the degenerate representation is what is most of the work in this paper with Gianluca. And this is when the representation, the image of the representation fixes a point. I can take the point to be infinity in CP1. And then, so we are basically looking at affine, complex affine transformations here and a representation to that. Okay, and remember that when it's degenerate, you need at least one apparent singularity. So there's at least one puncture with trivial monodromy around it. And the strategy here is to construct a complex, not only a complex projective structure, but to construct a complex affine structure with that holonomy. So the affine structure is one where you have, let me just mention, you have charts to the complex plane and transition maps. So again, this is an example of a geometric structure or a GX structure, transition maps in this affine group, affine of C. Oops, I ran out of space here. Right. And one of the theorems we got along the way is that if you have at least two punctures, then every non-trivial representation to affine group is the holonomy of some complex affine structure on the punctured surface. Okay, so this is maybe a slight refinement in the case where the monodromy lies in affine groups, but here you need at least two punctures. And there are counterexamples if you have, just one puncture. And I guess I'm out of time, so let me just sort of flash these images. So our method is very hands-on, very concrete. So we have to draw these fundamental polygons, if you like, for these complex affine structures on the plane. And these are some, so we have to draw some polygonal domains whose sides are identified with the given complex affine maps. And we have to make sure that it bounds some immersed region. And let me just mention there are some complications. Of course, it's a relatively tedious business. And so we have to sort of introduce various gluing constructions to do this. And we have to also use the mapping class group action on the representation variety to choose good bases for our fundamental group. Okay, and let me just sort of quickly mention that, we not only show that if you have a row satisfying conditions that there is some complex projective structure, in fact, there are infinitely many. And it's still and some kind of open problem. I'll skip these now, and let me go to the open problem about what happens to the, what does the fiber look like of these whenever this fiber is non-empty. So let me just write down the map again. This is from the space of projective structures on a punctured surface to, let me write this as the PSL2C representation variety or character variety. Is the representations up to conjugation. And you can, so if you take something whose some image, some representation here whose fiber is non-empty, which we characterize by a theorem, you can ask, what does this fiber really look like? I mean, so how can you describe the complex projective structures appearing in the fiber? And how can you go between them? And is it always discrete, for instance, etc. Okay, and so all that we can say from our work is that these are infinite fibers. And in the case of a thrice punctured sphere, this is now some recent work. This has been done to a large extent, perhaps sort of understanding these fibers very well in this recent work of Ballas, Bowers, Casella, and Ruffoni. And in the case of a closed surface, this was also an open problem for a while, and there was a series of papers by Shinpei Baba, who also understood these fibers for generic representations. Okay, let me now get into other directions, and thank you for your patience. And thanks for listening.
So thanks to Subhojoy for a wonderful talk, beautiful mathematics.
Thank you.
So are there any questions?
What are the references?
Subhojoy is not unmuted. Unmute yourself, Subhojoy.
Oh, thanks. Thanks for pointing out. So yeah, so this paper is on the archive. So I can send it to you if you like. And this paper, which dealt mostly with the non-degenerate case and with using Fogg-Goncharoff coordinates, this is a paper that was published last year in the Journal of Topology. And in general, for complex projective structures, there are some excellent, there's one excellent survey article by David Dumas, which I would recommend. So for complex projective structures in general, there's an article, it's a survey article by David Dumas. And the other references I think we can find in our paper as well.
So I have a question. So what? Yes. Just go up in your theorem. What is the so inside the space of the space of representations of pi1 inside PSL2 that has a variety structure or something,
right?
So what is the image of the space of CP1 structures inside that? What kind of subset do you get?
Right. Yeah. So that's a good question. I mean, in some sense, I mean, this is like I should mention that non-degenerate are already dense in the space of representations. So we kind of, we have, like Poincaré kind of observed, in general, a generic point is covered. So but I don't know any better other than, this description.
Is the image like a Zariski open subset?
Yes. So yeah, it's actually also not just Zariski open, it's actually open in the topology of this PSL2C, like the usual topology as well. That's a theorem. Well, okay, so let me, okay, so
you're not looking at topology of PSL2, but rather the topology of representations of pi1 inside.
Representations of PSL, so which arises from the usual topology on PSL2C. Because here, since you're talking of representations of the free group, it's just like PSL2C to the power of the number of generators. That's the space of representations. Okay, so so the space of representations is just a power, and I think, okay, so it's a good question, and I think it is known that the set I'm describing is indeed open. I mean, so this is like what I'm throwing out are actually some kind of codimension, analytic submanifolds with some codimension, positive codimension. So it's going to be like a but I haven't sort of thought about any other structure that this image might have that
I see.
Yeah, but I should mention that if you look at non-degenerate representations with no apparent singularities, that's one of the thing that appears in the context of my earlier paper last year. It appeared last year, but so there, these subsets of the character variety one gets are kind of thought of as, you know, some kind of cluster varieties, and so unions of cluster variety, because every time, so remember there was a complex torus in the picture when I talked about the Fock-Goncharov coordinates here, and so here in this moduli space, there's a lot of these, you know, these complex tori sort of sitting around for every choice of an ideal triangulation, and so there is, I suppose your question, you do have some sort of there are things that one can say. I mean, so there is a sort of there is a better answer to your question. So, which I'm going to provide. Yeah. So the cluster algebras, cluster varieties are the original context in which Fock-Goncharov's work arose, and they did it in a much more general context, not just for PSL2C, but for PGLNC. But for this particular work, I mean, we only need the case for PSL2C.
So perhaps if instead of quadratic differential, if you were looking at some higher power of the canonical bundle,
Yeah,
then you will be looking at some higher PGLN. Is that right?
Yeah, exactly. That's right. So that was what I, you know, thanks for pointing out. So I kind of mentioned it as other directions at the end. There's something called SLN opers, which are now, you look at nth order differential equations where the coefficients are no longer just quadratic differentials, but they are holomorphic sections of higher tensor powers of the canonical line bundle. And then you would have monodromy to PSLNC. And it's still very mysterious what the image is. So it's not going to be unlike the case for PSL2C, where the image was almost the whole of the space of representations. Just for dimension reasons, it is known that the image would be very sparse. It will be a positive codimension set. But what that set really is quite mysterious. And maybe some of these methods can be sort of these techniques can be generalized, because Fock-Goncharov coordinates are there even for PGLNC or PSLNC. And so maybe some of our geometric methods can be generalized to sort of study this set as well. So that was the other direction that I wanted to mention.
Mm-hmm. And it's, I don't know, instead of canonical line bundle, if one takes some different holomorphic line bundle, can one do some of these questions make sense in that setting? I don't know. I mean,
yeah, I mean, so I should have also mentioned the general context that this differential equation really represents a flat connection on a vector bundle over the Riemann surface. Okay, so like prescribing the differential equation is like prescribing the flat connection. So I guess yes, you can talk of monodromy whenever there is a fiber bundle with some flat connection, a flat fiber bundle, if you like. So, but yeah, so yeah, but I don't know whether, I mean, what the questions there might be.
Okay. Thanks. So, any more questions? Okay, I think if not, let's thank Subhojoy again for a very nice talk.
Okay, thank you very much.
Thanks, Sudarshan, for chairing this talk also. Maybe we will see you again sometime. To you both. So Ganesh, and can you stop the recording and live streaming? Not recording. Huh.
Okay.
So stop the live streaming also.